All right, question I actually got asked quite a bit when we switched online to COVID was about dielectric constants, and there's a lot of confusion about what constitutes a high K versus a low K dielectric constant. And if you're looking for like a hard number, I say, well, this number is the shift. The answer is that's not a thing. Dielectric constants are a spectrum. They're like polarity. And you can have polar molecules that don't act like polar molecules. So methylene chloride is a great example. The CHCl3 does not dissolve in water. Water we know is polar, but methylene chloride is considered polar. So same thing's true of dielectric constants, is that when we talk about dielectric constants, they're a spectrum. And what this spectrum does is it dictates what's most likely to occur. So when students say, well, how do I know which solvent to pick? There's actually a lot of considerations that go on here. But particularly if you're given like a multiple choice question, what you'll typically see is that one compound has a dielectric constant much different or much higher, much lower than all the others. Not a good strategy for real life, but for test taking, that's kind of what you do, is you look for the one that looks like the exception. So how do you do this outside of a test taking strategy? Well, first thing you need to consider is what's the highest K dielectric solvent I can work with. If I want to, if I'm trying to drive like an SN1 pathway or an E1 pathway, I want a high K dielectric. So this is looking at something like water, tetrahydrofuran. These are all good examples of things that, I think it's tetrahydrofuran. Should have looked it up before I did this video. But anyway, water is a fantastic example of something that has a really high dielectric constant, and it's very good at stabilizing unimolecular pathways. So if you want to find something that promotes that unimolecular pathway, look for solvents that have dielectric constants close to water. There are plenty of polar aprotic and polar protic solvents that resemble water very well. If you want to go the other extreme, you want to go towards a bimolecular pathway, the other extreme I like to work with are hexanes. Pure alkanes are definitely terrible at stabilizing charges because they're these big floating blobs of electron density. They don't have any polarity to them. So if you look at the dielectric constants like hexanes or diethyl ether, anything close to those are going to drive the bimolecular pathway. Now, in practice, there are other things we have to consider, because let's say you want to do an SN2 substitution. And we'll do butanol, and we want to replace it with sodium bromide to give us 1-bromobutane. Well, you may sit there and say, well, I want to do this through an SN2 pathway, so I should pick something like diethyl ether. Well, here's the problem with working with diethyl ether. It's very volatile. This is a reaction that would have to be driven at high temperatures to promote, because that SN2 pathway is kinetically sluggish. You need to give it heat. So you may not be able to run it at a high enough temperature. So you start with diethyl ether and say, okay, diethyl ether will give you the SN2 pathway, but it's not very good at dissolving the sodium bromide, which is what I need. And it's very high volatility. So if I want to switch to something that's got a lower boiling point, I'll look through a table of solvents to see something that has a dielectric constant close to that of diethyl ether. When I say close, like 10, 20 units. And I would look for something that's as polar as I can get within that dielectric constant. Now, let's say I want to do rearrangement here. I want to go through the SN1 pathway. Well, I would do this in water, but in-butyl ether or in butanol is not very soluble in water. So you may say, well, water is too polar, but I can find things around it that have the same dielectric constant or comparable dielectric constants, but will actually solubilize the butanol. So these are just factors to keep in mind. There is no hard line for dielectric constants where one is definitely SN1 E1 and one is definitely SN2 E2. With these mechanisms, we are typically promoting one pathway over the other. We're going to get a mixture of substitution and elimination. The question is, how do we ensure that the majority of our product is what we want it to be? For the dielectric constant effects of the solvent, we typically, I would again use water as one extreme for unimolecular pathways, SN1 E1, and diethyl ether hexanes as the SN2 E2, and then pick things around those numbers, close to those numbers, to kind of promote those types of pathways. And again, keep in mind, in the real world, you would have to turn around and also make sure that the stuff you're working with is actually soluble in the solvents you're working with and are viable at the temperatures you'd be working at.